Hello, welcome to Science Pub. Please take a moment to introduce yourself in the chat and tell us where you're tuning in from. We have participants from all over our coverage area, all over the country and the world attending our events, and we'd love to hear where you're tuning in from. Use the chat feature to ask questions of our guest speaker throughout tonight's talk. If you're watching on YouTube and you don't see that chat feature on your end, that means you're in full screen mode. So to exit out of that full screen mode, just click the bottom right part of your screen and the chat should appear on the side. You can use that to ask questions. If you're watching this on Zoom, use the Q&A feature to ask those questions and we'll do our best to get to all of your questions. So welcome to Science Pub, a monthly series exploring the fascinating scientific world around us. I'm your host, Nancy Coddington, Director of Science Content for WSKG Public Media. This season, we have a great lineup of speakers and topics, ranging from mental health to medical cannabis to exploring the science behind fire and firefighting. Tonight's talk is Sounding the Alarm, Milestones in Fire Science. Our guest speaker is Assistant Fire Chief Rick Allen Jr., and he's going to be sharing why today's house fires are so dangerous. Construction is nearly airtight, homes are filled with hydrocarbons or plastics, and real wood furnishings are less common. The result is a fire that burns hotter and faster than decades ago, producing smoke that's highly toxic to us and firefighters. Tonight, we will compare past fires and firefighting to the technology of today. We will view a video from the new WSKG documentary, The Devil's Fire, and a discussion with local filmmaker Brian Fry. We'll learn about the 1913 Binghamton factory fire, which killed 31 people, and New York City's Triangle Shirtwaist factory fire that claimed the lives of more than 100 people just a few years prior. We'll see how these tragedies deepened our understanding of fire science, created new safety regulations, and changed the way we fight fires. Rick Allen Jr. is Assistant Fire Chief for the City of Binghamton Fire Department. He started volunteering as a volunteer firefighter at the very early age of 16. He began working for New York State as a fire instructor in 2016. Rick has been with the City of Binghamton Fire Department for 28 years. Welcome, Rick.
Thank you, Nancy.
I'd also like to welcome WSKG's filmmaker, Brian Fry. Brian has been with WSKG for 30-some years, and he tells our local stories that also have a national impact. Welcome, Brian.
Hi, Nancy. Good to see you.
Well, thank you. I'm so glad to have both of you here tonight. Brian, I want to start with you. So can you tell us, about why did you want to tell this story, this part of Binghamton's history? Why was it so important?
Sure. Thanks for asking. So I grew up in the Binghamton area. I was born and raised here, and I've always loved history. About 15 years ago, I became a member of the Broome County Historical Society. And I'd heard about the story about the Binghamton clothing factory fire for many years. There's a marker at a cemetery on the first ward of Binghamton that I had seen a number of times, and I was, as I researched the story, I was always really interested in the fact that, besides the fact of tragedy that 31 workers died, but that the building collapsed so quickly. From the time it was spotted till the time the building collapsed was only 18 minutes. And so when I started making films, I knew that at some point I wanted to make this film, but I remember going to the Historical Society and I was somewhat disappointed at first with some of the visuals that were there. I didn't think I had enough visuals to tell the story. But over time, every time I was researching another film or something like that, I would and if I find a picture, I would put one aside. And so it got to the point where I realized I thought I had enough material to tell the story, which probably along with the 1935 flood in this area is probably the second, or combined the two, are probably the two most tragic events that happened in this area. So that's why I wanted to tell this story.
Thank you, Brian. Do you want to cue us up for the video that we are about to watch?
Oh, sure. So the film is about 90 minutes long. But what I did is I pulled 7 minutes out about the middle of the film. It actually is when the fire starts, and it talks a little bit about how the fire spread so quickly through the building. And I think hopefully this will give us a good setup for Rick's chat. So if we can roll that clip now, that'd be great.
By noon on July 22nd, the floor of the factory's sewing room was covered with piles of discarded material. A slight mist of fabric dust hung in the air. The girls were tired and hot, looking forward to the lunch break when the entire plant shut down for an hour. The factory's engineer, John Schermerhorn, who worked in the building's basement, finished bundling the scraps tossed down the building's fabric chute. It was Schermerhorn's job to collect and sort the scraps, stuffing larger pieces in canvas bags and burning the smaller bits in the company's furnace. The discarded fabric that littered the sewing room, however, would still be there when the girls returned from lunch. That material wasn't scheduled to be collected until later that afternoon. It was 2:28 p.m., Tuesday, July 22nd, 1913. As the doors opened, sales clerk Reuben Hall, panicked and obviously frightened, immediately confronted Fuller at the elevator, screaming, "We are on fire!" Fuller turned to the stairs and saw a small fire on a shelf mounted 7 feet above the steps to the basement, the same stairs he had walked down moments before. The fire was contained to one small corner of the shelf. Fuller yelled, "Fire!" and drew the attention of Reed Freeman in the front office. Fuller and Hall then reached for water buckets on a stand near the stairs. Reed Freeman arrived at the stairs as Fuller and Hall were attempting to throw water up at the fire above their heads. "I was certain," Freeman later testified, "that the water buckets would extinguish the fire. It didn't look very big." Fuller and Hall's attempt missed the flames. Freeman was then suddenly hit with a splash of water from above. At that same moment, the 4 men working in the second-floor cutting room had spotted smoke rising up from the stairs. Cutting room foreman Albert Decker, thinking fast but unfamiliar with the operation of the fire alarm, pressed and held the alarm button, triggering a single bell pulse, unlike the double alarm pulse the company had been trained to react to. The other cutters, Earl Johnson, Frank Freeman, and James Fuller, each grabbed fire buckets and threw water down toward the smoke and flames beneath them, splashing Reed Freeman below. The cutters' attempts missed the fire also. In the days to follow, it would be discovered that mounted within reach of the cutters, purchased and forgotten years before, was the company's lone fire extinguisher. It had never been used or tested, and had gone undetected during 3 separate fire inspections. The fire quickly spread to the rest of the material on the shelf and began to ignite the wooden steps and railing leading to the second floor, beginning to cut off a major route of escape from the floors above. Amber Fuller yelled to engineer Schermerhorn in the factory's basement, "John, we are on fire! Get out now!" Schermerhorn started up the steps, then stopped, backtracking again to the basement. Fuller later testified, "I knew he was going back for the money. The last I saw of him was on the bottom steps of the basement." A wood-framed glass transom above the stairs suddenly collapsed onto the steps, cutting off the exit from the basement. Freeman yelled for his wife to call the fire department. Her first attempt to reach an operator failed. She reached for another phone. Meanwhile, Reed began moving raincoats hanging near the stairway to keep the fire from spreading. But it was too late. It was already out of control. Kindled by the strong breeze blowing through dozens of open windows, feeding itself on fabric cuttings and fiber dust, the fire found a rich source of fuel in floors waxed in paraffin, and the network of wood beams and rafters that spanned the entire building. The inferno quickly seeped into the veins of the factory. Within moments, relentlessly seeking a conduit for cooler air to heat and breathe, the flames shot up the elevator shaft and the fabric chute, waiting to release, like a bomb eager to detonate. Then, without hesitation, Dimmick ran to the 4th floor. The scene in the sewing room was confusion and disbelief. Some workers remained standing behind their machines waiting, as instructed, for a second alarm. "We thought it was a false alarm and no one rushed," Ruth Crotty later testified. "We all laughed and took our time and walked out slowly. Then the fellow that fixes the machines came up the stairs clapping his hands, telling us to hurry." Nellie Connor was cleaning a stain off a jacket when the alarm rang. She then saw Sidney Dimmock arrive at the top of the stairs. "I think when Nellie saw Sid's face," seamstress Mary Hogan later testified, "she knew we were all in bad trouble." Nellie joined Sidney at the stairs, urging the girls to hurry. Smoke began to drift into the room through the fabric chute. A group of girls hurried down the stairs and made it to the street. Others stopped to grab purses and shoes. Some, remembering the teasing during the drills, stopped to change. A second group started down, but Juliana Lakey, whose nightmare had become real, briefly fainted on the steps, slowing the escape. At that moment, flames burst through the floorboards near the third-floor stairs, blocking the only path down to the second floor. Workers scattered to find another way out. Many would later recall seeing Sidney Dimmock guiding workers and helping carry several women to open paths through the smoke and flames. Nellie Connor never left her post on the fourth floor, calmly telling her girls they'd be okay, urging them to hurry, guiding their arms and tossing chairs away from aisles. Ruth Crotty and her sisters became separated in the confusion. "Lucy went out when the fire first started," Ruth testified later. "I went down one flight, but the smoke and flames drove us all back up. There was nowhere to go." She watched a group frantically pressing the button for the elevator. When the door opened, an explosion of flames enveloped the women, setting their cotton dresses and hair on fire. Ruth screamed, ran to a window overlooking the field by the post office, and jumped. 50 workers were at that moment trapped on the third and fourth floors with dwindling options. As the smoke and flames grew thicker, a group headed to the back of the factory and their last hope, the building's fire escape. The time was 2:34 p.m.
That all happened so incredibly quick. Brian, can you talk a little bit about, how did you go about the research for this documentary?
So a lot of my research was done reading old newspaper articles around the time of the fire. One of the things that the fire was so heavily covered in many newspapers at the time, it made national news. And a lot of reporters came to Binghamton to talk to people, talk to survivors. I combed through dozens and dozens of newspapers, and that's where a lot of the detail comes from first-person accounts of where they were. And as you could see, between the time the fire was first spotted to the time when people were already trapped was only 6 minutes. And that's why I was fascinated by how quickly this fire spread through the building. And that's when one of the first phone calls I made was to the Binghamton Fire Department. And people like Rick and his colleague were really helpful in kind of talking to me about how buildings were made at that time and why this fire spread so quickly.
It certainly did spread very, very quickly. If you have questions for Brian, please put those into the chat, and we are going to come back to Brian in a few minutes. Rick, this tragedy was 100 years ago. What was some of the science that made this fire so devastating?
Well, some of the things that made this fire obviously a tragedy in our area was the fact of the fuel load, as I talked about in the film. All those scraps of cloth that were left on the floors, lack of any kind of fire suppression systems, no sprinklers, no fire hoses, one extinguisher they didn't even use or knew existed. And then the building construction itself, open stairwells, only one stairwell, the elevator shaft, the chutes that they disposed of the materials in, as I said, using paraffin wax to care for the floors. And all of that just grew into the fire load that was fed by all the open windows that they had to try and keep the building ventilated in the hot July weather. That just helped make it a wind-driven fire, increase the flames, increase the heat release of the fabrics, and of course the structure itself. Even though the exterior of those buildings was masonry. The interior floors, the beams, everything was wood. So the building itself was a fuel load.
Yeah, it was just kind of like a big candle. Thank you. We are going to go right into Rick's presentation, talking about the science behind fire and delving a little deeper into this topic.
All right, so what I'm using is I'm using a PowerPoint that was actually designed to teach firefighters about fire dynamics and the basics of fire behavior and fire science. So we took some excerpts of this to try and share with you during this program. So to help firefighters stay safe, some of the things is to teach them about what fires do, how buildings burn, what we expect the fire to do, where it's going to go, how it's going to behave under certain conditions, and how our operations impact them so that we can prevent doing things that may get trapped victims or ourselves hurt or killed. So first, to get into this, we were going to talk about some of the physical science stuff. So obviously, we talk about matter. It has mass. It can take different physical shapes. Solid, liquid, gas. Obviously, it could also change chemically when it's met with fire, and some of that happens through the chemical chain reaction that occurs when combustion happens. Part of combustion is oxidation. Oxidation, even rust, is oxidation. Smoldering fires, it's a type of oxidation without any flame showing. And then as we get through rapid oxidation, a very rapid oxidation would be seen in an explosion. So oxidation is a big part of fire. Another part of fire is energy, where that energy comes from. And usually that's a fuel. What we talk about in potential energy is our fuel load, how much energy it has to be able to release. So here we're just seeing a stack of pallets of wood. It's our potential energy, and when they are on fire, it's that kinetic energy. It's that energy being released in an exothermic reaction. And there's a picture, showing an exothermic reaction. So it's releasing energy in the form of light, which we see as flame, and heat, and that's the energy being released. An endothermic reaction is where that heat is absorbed by cooling of water, and then that water is converted to steam, which obviously is the primary reason that we use water as an extinguishing agent. So for years, we were taught in the fire service about the fire triangle: oxygen, fuel, heat. Three things that every fire needs. And they're also the things that we use to fight fires. So if you want to put a fire out, you can remove the oxygen. It's like taking a cooking fire and putting the lid over it, or taking a candle and snuffing it out. Removes the oxygen, the fire can no longer breathe, it goes out. So you remove any side of the triangle, fire goes out. Remove the fuel. If the fuel runs out, fire goes out. And then removing the heat, which as firefighters, we typically use water, which cools the fire, thus putting it out. Some years back, probably about 50 years ago, science showed that we were better off using the fire tetrahedron. The fire tetrahedron added the chemical chain reaction. The chemical chain reaction is important also because it is the ongoing development of the fire. As the molecules begin to move and radiate and rapidly move faster, that continuous reaction creates an ongoing fire. What they found out is that certain chemicals will also stop that chemical chain reaction. So a gas like halon, if you apply that to a fire, the fire goes out. So it's not just as simple as removing the three sides of the original fire triangle, but now they added the fourth side, and basically it's like a pyramid. Remove any one side and your fire goes out. So this is the real basics of fire. Then we get into pyrolysis and vaporization. Most people do not understand that when you see fire, when you see flames, it is not the solid material that is burning. For anything solid to burn, first it has to go through pyrolysis. Pyrolysis is the gas coming out of the solid object. So you are converting that solid object to a gas, and it's the gas you actually see burning. So the heat is exposed to irradiated to or conducted to, we're going to talk about those in a moment, to our solid object. Our solid object, the molecules begin to rapidly vibrate and move around quickly, creating more heat, and then off gases, and those gases are what actually ignites. Same thing in liquids. the liquid has to become a gas first. And when you're speaking liquids, that is called vaporization. Got a quick little video here of pyrolysis just to show that basically it is the gas that burns, not the solid material itself. So what you're seeing here is this is just a fire demonstration. A firefighter in a laboratory has taken some wood shavings, put them in the bottom of this glass flask, and he's heating it up till they begin to pyrolysize, and they begin to release a gas. And then he'll see him. He will take a lighter, and he'll be able to ignite the gas that's coming out of the top of this flask. And that is showing that those vapors are indeed flammable. And that is what's burning, is the gas. The wood doesn't burn, it is the gas. A few clips here, you will see where the flame actually gets enough oxygen concentration down inside the flax where it flashes back down in where the rest of the gas is. But you'll notice the wood doesn't burn because it's not hot enough to continue burning inside the flask. It needs more of that gas and more of an oxygen mixture too. So you'll watch here in a moment, you will see it flash back down into the flask. But you can clearly see there that it's the vapors of the wood. There you go. So you can clearly see there that those vapors is what is burning, not the wood itself. So when it comes to flaming combustion, you have to have a heat source. It's going to pyrolyze your fuel. It's going to create those gas. They mix with oxygen. You have to have a proper mixture of oxygen. We'll talk about that briefly in a little bit. The gases ignite. They create your fire. Combustion products expand now because it creates different products in the smoke, and we'll talk about that also. It's going to fill up the compartment. That fire continues to generate more heat, which transfers to more gas-producing products, and it just continually is a cycle now. Oxygen is pumped in, combustion is pumped out, and it's a continuous fire. And here's kind of a picture of that. So you've got your fire, your exhaust, your products of combustion flow up as the heat helps them move upward. And then you have a constant movement of air inward, bringing in fresh oxygen to your fire. So when your fire is burning, it produces things. Most people just think of smoke. But the things that are in that smoke, most people do not understand. So obviously, you're producing heat, and then your smoke. In your smoke, there's going to be a lot of different toxic gases. Some of those toxic gases are lethal to humans. Some of those toxic gases are also flammable. Some of those gases just displace oxygen, in which basically human beings obviously cannot survive without oxygen. And then some of the smoke is particulate matter. It's aerosolized. It's what's called incomplete combustion. So when you really see smoke, it's incomplete. If you think about your typical natural gas burner on a stove or in a furnace, you see that blue flame. That is an efficient fire. It's burning. There's no smoke. You've got the nice blue flame. You don't have the orange or red flames. When you have the orange and red flames and smoke, that is incomplete combustion. It's not efficient. When we have a structure fire, though, those unburned fuels in the smoke have much more of a potential to burn and become a fuel. Also, the toxins and things that are in the smoke are more than you would just see in a typical fireplace or a campfire. Because of all the things that we have in our businesses and our homes, those multiple products burn. And when they burn, they mix and they create different chemicals and gases in the smoke. They become very toxic to us humans. So incomplete combustion, more smoke. And especially when you start talking about the plastics, that we have so many hydrocarbon type fuels today in our buildings, plastics, rubbers, and we'll talk about that a little bit more also. Generally, the gases that you see are colorless. It's the vapor and the particulates that you see. Even some of the particulates that are actually in the smoke, the vapors that are in there are actually water vapor because wood contains moisture, but it comes out in the smoke. So you're getting water vapor. You're getting the particulates of the incomplete combustion. You're getting all the gases. And the smoke color is going to be different on the fuel and the smoke toxicity. And the chemicals it's creating are going to be based on the fuel and how different it's going to be. Here's just a small list of some of the chemicals that are in smoke. So carbon monoxide is the one I know most people are aware of. Any gas-fired appliances in our homes or even wood stoves can produce carbon monoxide. So most of us are used to understanding that carbon monoxide is produced through fire and combustion. Some of the others, though, that we meet in the toxic smokes that are in our businesses and our homes when they burn is formaldehyde, hydrogen cyanide. I'm sure a lot of people know cyanide as being a very deadly toxic substance. Nitrogen dioxide, and then of course the particulates, and those particulates are not only able to block our trachea, block our nasal passages, but they're the little pieces that make up what a lot of times you can see in the smoke, because most of the gases are usually colorless and invisible. Sulfur dioxide is another gas. Speaking of the particulates are one of the I guess you could kind of say good things in the smoke, because it's what allowed us to create things like smoke detectors. Smoke detectors and smoke alarms operate on detecting the particulates in the air. And when the smoke detector finds those particulates, sees them, senses them in the detector, that's when it sounds the alarm to let us know that there's a fire and alert us so we can get out in time. Besides those gases, there's a lot of other ones. They're just pretty much countless and nameless, the different combinations that come out through the different materials that we have in our houses and businesses that burn. So many of these combined, they make lethal doses. That's why most people that die in house fires, they die from the smoke inhalation. They don't die from the fire itself. It's usually smoke inhalation. Speaking of carbon monoxide, some little fact that most people don't know is carbon monoxide can be a flammable gas. If it's in the right mixture, gets enough oxygen and gets heated up to high enough temperatures, so it says here 1100 degrees, it will ignite, sometimes explosively, depending on the proper mixture of oxygen with it and the temperature. So with all the different gases that are in the smoke is fuel. This is something that we are trying to teach firefighters over the last 20 years, making them understand that some smoke, it's oxygen deficient, it contains chemicals, may be acutely toxic. And then, of course, there's a lot of carcinogens in smoke, too, which has become a big concern in firefighter health and safety over the last several years. But smoke being fuel is the thing that we're trying to teach to firefighters these days and make them understand this. Here's just a real quick little video that we can show. So this is some superheated smoke coming outside of a training trailer. So they're using like a Connex box. This is in Sweden, and they're doing a training. And you can see the smoke pushing out of the box. So it's got the heat. It just needs the right mixture of oxygen. So once it gets outside, there you go. And as you can see, there was no other fuel there except for the smoke and the gases that are in it. So we're trying to make sure that firefighters understand that. When it comes to these gases that are flammable, they can spread throughout our structure, and it creates pressures. And pressures are going to teach us something about flow paths that we're going to hear about a little bit later in the presentation. So as you can see, the fire is burning in the chair. That heat is lifting upward, and it's creating higher pressure in the upper areas. And then convection causes it to flow away from the fire, and it's going to find a vent point to leave at. That same vent point is going out. It's going to try and bring in cooler, fresher air into the base of the fire to help feed the fire. It's a continuous circle. Heat is going to transfer to things around the room, and this is what's going to cause other things to ignite and cause our fire to grow. We talk about heat transfer. There are several simple methods of heat transfer, but the one thing that's always constant is that heat always travels from warmer objects to cooler objects. No matter what, that's the way that it works. So the warmer objects are going to heat up the cooler objects until equilibrium is reached. So the way that heat is transferred, one is through conduction. Think of through a piece of metal. Even think about electrical conduction, like your toaster. When you watch the little wires in your toaster glow red hot, that's a form of conduction. When you're using a skewer to cook a hot dog, that skewer heats up and will cook the hot dog also from the inside. So that's one way that heat can transfer, is through objects that conduct heat. Metals are usually the best conductors, masonry items less so, wood and other moisture containing items even less. So this just shows some different types of things and how they conduct: steel, concrete, gypsum, wallboard, which is very low conductor. And that's why we use it to protect structural elements of our wood frame homes and businesses. Next is convection. So convection is taking the heat, and it goes through the air. It travels along with the gases. So this thermal energy is being circulated by the movement of the air. Remember, we were talking about before about the pressure. That's what's causing that convection. The pressure of the fire going up and that fresh air coming down below and coming back in is causing that convection. So it's not just the smoke that's moving, it's also taking that heat with it, and that is what's called convection. So one thing to understand about convection is it can move vertically, it can move laterally, and it all is going to depend on the fire and the entrance of fire, of the flow of fresh air coming in. Radiation is probably the most common method of heat transfer, especially when it comes to structural fires. So as you can see here in the picture, the radiation is being radiated in all directions from the fire, and then it also gets radiated back from things that it's heating up. So the fire is heating up the ceiling, the walls, other objects in the room. They are also going to continue to radiate away. Even before they begin to combust, they will begin to radiate that heat, warming up other objects in the room. So when it comes to radiation, it's actually the energy being transmitted as electromagnetic waves. They become the dominant mode. So even if there is convection going on, the radiation is going to be the primary means of heat transfer. It can travel some distance from the fire, and we will touch on that a little bit later also. Some of the things that can affect the influence of that radiant heat is the nature of the exposed item. So what is the exposed item? Is it wood? Is it gypsum board? Is it something metal that's going to also allow more conduction of the heat? And what about distance? How close is it? How far away is it? What is the temperature of the heat source? What is its heat release rate? So the interaction of all the different methods of heat transfer: first, the fire is going to radiate heat, then there will be some convection, then there will be some conduction, and then it's going to ignite new materials, and those new materials are going to radiate, and the cycle continues on. So some of the chemical content is going to affect the heat of combustion and the heat release rate. So you can see here, like a small waste basket, the peak heat release rate is 4 to 50 kilowatts. You start getting up to a small pool of gasoline, 400 kilowatts. You start getting up to a polyurethane sofa, you're talking 3,120 kilowatts. So, even your sofa in your living room is far more deadly than a pool of gasoline. And then look at the Christmas tree, the dry Christmas tree. This time of year, that's definitely something we should be paying attention to. Live tree, make sure you're watering it. 3,000 to 5,000 heat release. So something we should definitely pay attention to. And the difference between a lot of these things is because of the hydrocarbons that are in them in some of today's materials. Energy transfer rates are also based on the power that's being released and how much there is. So a candle, a candle like that will probably put out about 40 to 60 watts. Your trash cans can start putting out kilowatts, and then your couch will be putting out megawatts. What else affects how solids burn is their surface to mass ratio. I think anyone can agree that if you take some fine sawdust or some coarse sawdust, it'll burn quite quickly. It's going to ignite quickly, and it's going to burn and be gone a lot faster than a log. A solid piece of wood is much harder to ignite, and then it will burn much longer. So its heat release is going to be slower. What's also important is orientation. So if you were to take a board and set it on fire in the corners in the picture on the left, fire doesn't like to spread horizontally but now all of your energy is going upward. So your convection is not helping, and your radiation is going to help either that much, because it's very limited, because a lot of the radiant rays are going upward and outward. So you're losing some of that energy. So it's going to be very slow to spread across the horizontal surface. Vertical, very different. Here, now the convection and the radiation is going to be increased and burn up your board. This fire, again, being heat likes to go up and out. Oxygen, as we talked about in the fire triangle, fire tetrahedron, very, very important. Oxygen is the primary oxidizing agent in a fire. Typically, most air has 21% in it. Fire can survive into, I believe it's as low as 14% oxygen. And the more oxygen is available, the quicker the fire can burn, because the energy release increases in the fuel source.
Rick,
So,
I actually have a question about that. So,
yes.
As firefighters are coming into a building, they'll open windows or make holes when fighting that fire, which is then allowing air to come in and feed that fire. Can you talk a little bit about that?
Yes. So what we call ventilation is technically called tactical ventilation. It's supposed to be coordinated. So we want to coordinate it more with when we're bringing our hose lines in, so that as we are feeding the fire, we are able to extinguish it quickly. And that's something that actually I do have a little bit more to talk about towards the end of the presentation. Yes, we do need to get the heat and the toxins out of the building, because what that's going to do by us releasing them into ventilation is it's going to lift what we call the plane, so that way we can lift the smoke and the heat up so that we can see under it. It gets cooler. And if there are any victims inside, that may also give them space beneath the smoke if they're crawling, to maybe have a little more area of fresh air. But it also could be dangerous, because now what we've learned through science is that we're creating more and more flow paths, which we're going to talk about more at the end. So ventilation has to be something that firefighters train on, practice, and has to be coordinated.
Thank you. And I have another question about when you were talking about that surface area, right? So you have sawdust or flour or fibers that are in the air. Let's say, for example, in a factory.
Correct.
How do factories take that into account and mitigate those flash points?
So these days, people are much more aware of those issues. A lot of places like woodworking shops have systems set up where they've got those areas that utilize a lot of sawdust, and they are ducted to dispensers that are actually exterior of the building. So they go through a system of blowers, vacuums, fans, whatever it may be, and are taken to via ductwork typically, and stored in hoppers that are typically on the outside of the building in most cases. Sometimes they need to make sure that they're maintaining those areas also. I know we had a fire in the city just a couple of years ago, a facility that cuts a lot of cardboard, and it was actually the cardboard dust that caught fire. They did have a system that sucked most of it into a hopper to the exterior of the building, but a lot of the particulates were still around the area where they goes into this duct system, and it did catch fire actually through spontaneous combustion, believe it or not, which can happen when it gets a certain amount of moisture, the right mixture of air, as it's basically decomposing and breaking down, and it started a fire. So it can happen, but more and more businesses, industry is aware of this, and they are doing things to their buildings to take care of that problem, so it's at least not in their buildings in most cases.
Thank you.
One of the things I touched on a little while ago was the vapor to air mixture, your gas to oxygen ratio. So sometimes you can have vapors that are too rich. So there's a percentage that almost any flammable vapor can burn in. They have a flammable range. If it's too lean, if there's not enough of the gas to mix in with the oxygen, it will not ignite. If there's too rich, there's too much of the gas mixed with oxygen, it won't ignite. But it has a happy area, flammable range as we call it. And your different gases have different flammable ranges. That's where sometimes, like I said, smoke is fuel, but which gases are actually going to ignite in it, you don't know. But once it does ignite and it pulls in some more oxygen as it's burning, all of them will ignite in a lot of cases. So sometimes it's just lucky that you don't know that. This also applies to natural gas and propane in homes. If they have gas in their home, you have a gas leak, many times it doesn't ignite because it's too rich. And sometimes it doesn't ignite because it's too lean. But when you get in that happy area, then you may have an issue where you could have an explosion or a fire. When it comes to structure fires, what's also important is the fuel and oxygen availability. Usually fuel is not an issue. We usually have plenty of fuel in our homes and our businesses. So usually it becomes ventilation limited fires that become a concern. And we're going to talk about those. First, though, I want everybody to understand the stages of fire development and how this all goes into it. So as firefighters, we are taught about the stages of fire development. So first is what's called the incipient stage, then the growth stage, then the fully developed, and then the decay. So typically, if you look at on the left, example A, that's what's called a fuel-controlled fire. If you will, think of it as your campfire. You ignite it, it catches fire, it begins to grow, it's fully developed, you got nice big flames. And then eventually, as the fuel begins depleted, your logs get smaller, become coals, it begins to decay, and then your fire goes out. What we found out, though, is that structure fires are different because technically they are ventilation-controlled fires because our homes are all closed up nice and tight. Back in the energy crisis during the 70s and early 80s, people started doing things to protect their homes and help insulate their homes, keep the heat in. So we got, double pane windows, we insulated our walls and ceilings better insulated doors, etc. So now when we have a fire, it becomes what we call ventilation controlled. So you have your ignition point, it grows, but then as that fire grows, it begins to run out of oxygen. It's sucking in all the oxygen and depleting it because its own products that it's creating, the gases and the smoke and the particulates, begin to actually choke out the oxygen also. So the fire actually begins to decay on its own. But then what happens is usually we show up and we're either opening the front door or a window to make a rescue to go save somebody, or simply opening the front door to go in and put the fire out. And this is when we're creating a flow path. And now that ventilation is being given to the fire, and now it goes right back into a growth stage until it's fully developed, sometimes causing flashovers and backdrafts. And then we've got to put that fire out. During the incipient stage of the fire in a house, this is the time when people can get out. And as you're going to see in a little while, we're going to watch a video, you've only got about 3 to 4 minutes really to get safely out of your home. During the incipient stage, these are the times when you can use a small extinguisher and possibly put the fire out. Once it goes to the growth stage, it's going to grow very quickly and you will not be able to put it out. You see flames, that's usually telling you that it's in the growth stage, it's beyond incipient stage. Growth stage is going to depend on the ventilation it gets. Most of the times you have, during the initial part of your growth stage, you're going to have plenty of oxygen available. Once it gets to the point where it's creating a lot of smoke, it begins to become oxygen deprived, especially as compartmentized. If it's in a room where there's a door closed, or it's a larger room that possibly the area where it's going to try and pull air from is too far away. So when we go from that, from the growth stage, the fire has that oxygen, it's going to move into rapid fire development, and then it may transition to a ventilation decay stage unless it gets more oxygen through ventilation. And that ventilation be created either by us or even through glass breaking, because if fire heats the glass and the window breaks, that may allow it to also create ventilation. Something else that happens in a fire is what we call thermal layering. So as we get the thermal layering in the fire, and I'll show you a better picture, you're going to see a plane that exists between where the smoke is and that the fire is down below and the fresh air is down below. And why this becomes an issue is because we talked about pressure earlier. You're going to have air intakes, areas where the air is being pulled into your building, and then your exhaust outlet, which is typically your fire, sucking that air in and then pushing it upward again. That's just a quick picture. So here's a better picture, an actual fire in a lab. So down below, you can see the neutral plane. Down below, you got fresh air coming in. You can see the fire. Your neutral plane is that perfect area that you can typically see between where all the smoke and toxic gases begin and down below where it's pulling that fresh air in. And up above, you can see the flames coming out. And a good example of, you can see the orange flame in the smoke. Again, showing you that it's those gases up above that are burning. But again, there's a lot of black smoke there. So all of it's not burning. Just some of it is, because as it leaves the room, it loses enough heat to actually ignite. And some of it's so thick, it may not have enough oxygen up there because all the oxygen is being sucked down below to feed the fire itself. So once our fire is ventilation limited, we may still have a lot of high temperatures in place. Maybe typically in those areas are not habitable. Anybody who's in that area typically would not survive that situation. The gases and fuel only need oxygen at this point to ignite. That's what they're starving for. Pyrolysis can still continue because remember, we're still have enough heat in there. So we're heating the objects in the room. They're still off-gassing. Those gases are still fuel. So the compartment fills up with black smoke and it's slowly cooling those fuel gases, but you can't see any flames. So what's it need right now? It needs air. It needs oxygen. So this is a photo in a lab of a firefighter venting a window. He is going to give that fire what it so desperately wants. He's going to give it some of that oxygen. So even though there's increased heat release rates in the room, the fire is still growing. He's created a new flow path by breaking open that window and allowing the air in. And here's just a quick picture. You can see that the fire in the top left is in its growth stage. Then it goes into decay all by itself because it's ventilation limited. It can't get enough oxygen. 5 seconds after someone opens the front door, you see the fire go right back into that growth stage. And then it goes into rapid fire development, has a flashover. And then as you can see in the bottom right, post flashover 60 seconds after the door is open. So within 5 seconds, it was growing. And within 60 seconds, it flashes over. So flashover is that rapid transition from growth stage to fully developed. We'll see a good example of it in a few minutes in a video. This is when all the combustible materials in the room and all the gases in the room, they ignite simultaneously. They've all reached their ignition temperature and they just ignite. And this is all through convection, radiation, pyrolysis. All these things are happening and they've got enough oxygen to do it. And you've got your flashover. So as it says, your upper layers are radiating heat downward to all your objects in the room. All the objects in the room meet that ignition temperature simultaneously. All the burning gases also increase. They are also burning. That fills the room's entire volume and the extent of any opening. So even if you've got smoke coming out in the hallway like you saw in the one picture, you will see fire travel out through that. And that's typically what we call a rollover. Rollover is an indicator of flashover. It's either about to happen or is happening and you're in another area. It's those unburned gases that are coming out. It's going to happen during growth stage. And, well, I'll show you exactly what it looks like. So this is a great video. It's from a firefighter's point of view from a helmet cam. He's crawling down a hallway. He's got his hose line ready. And you can see that smoke over his head. There's fire in that smoke. Years ago, they used to teach firefighters, you never put water on smoke, but nowadays they teach us to cool that before we even get to this far so that you don't have that fire traveling over your head. Because now as that fire is traveling over his head, it can create drop down and get fire trapped behind him too. But this is a training fire, so they're getting down here right to the seat of the fire where they're going to extinguish it.
Rick, how hot is that when you are below that fire? Like, are you feeling that heat coming through your protective gear?
Yes, we can usually feel that going through our gear. Typically, the Temperature at the ceilings on something like that is going to be well over about 1100 degrees. And our turnout gear, sorry, I'm just going to let that play again. Our turnout gear is able to hold back some of that, but believe it or not, it doesn't take much to cool down between those upper temperatures. Like I said, it'd be about 11 to 1500 degrees right at the ceiling level. Probably about where his head is at. I'd probably say you're at about probably 500 degrees. Down probably by his waist is probably about 300 degrees. Down at the floor, you're probably like 200 degrees. So our gear does protect us from a lot, but only for amount of time. If he was to stay in those conditions, eventually the heat would penetrate the gear. It would slowly saturate his gear and he would get burned. It doesn't protect us forever.
It definitely looks like that's toasty. Rick, we are getting near the end of our presentation, so if you want to, I know, fast forward maybe through a couple slides.
Yep,
I would love to see you play that video that you shared about living rooms and talking about the hydrocarbons there.
I'm going to play that one next. So we want to talk about fuel load and the fact that structure itself is fuel. Fuel loads these days have changed a lot in the materials in our homes. Used to be most of our furniture was made of wool, wood, cotton, wood. It was all natural materials. Nowadays, everything is hydrocarbons, and we have lots and lots of plastics. Some of the other things that affect fire growth are big open areas. More and more houses have open floor plans, and that allows radiant heat to travel further and faster than it used to. So it's a combination of everything: our tightened up homes, our contents of our homes, and the building construction itself, those open floor plans. So as you can see right here, you got radiation that can travel throughout that whole big open room, which is going to travel faster, and it's also going to even block off the smaller areas. Where if it's compartmentized, it's easier to control the spread of the fire, and then even when we get there, it's easier to extinguish it. So construction has made an effect, and we'll get into that one last thing. But here's the big one. This is the important one for everybody to see. So you're going to see here, this was just done in 2020, side-by-side burn, natural versus synthetic. So you're going to see the room on the left has got your more natural or legacy furniture, as we used to call it, mostly natural materials. The room on the right is going to be your hydrocarbons, your plastics, your polyurethanes, your nylons, your polyesters, etc. And you're going to see how quickly the synthetic room goes to flashover compared to the natural. So as you see on the left, our natural, we've got our fire started. It's getting beyond its incipient stage right now. It is getting into a growth stage, just slightly over a minute and a half into it. Our synthetic still doesn't look like it's doing much. It's still definitely in the incipient stage at this point. I mean, we're at the 2-minute mark, and we're just getting into growth over in the synthetic side. The things are about to very quickly change. And this is where, if you noticed, you didn't have smoke yet. So at the 2-minute mark, you had smoke. So your smoke detector is going off in your house. So you have to subtract 2 minutes off that clock. Think about how long you have to get out of your house before your living room gets to these kind of conditions. You can see that neutral plane there now between the smoke and the gases, and where the cool air is coming in and feeding the fire. Your smoke's beginning to bank down. That neutral plane is coming lower and lower. That's going to start getting to the point where it may start ventilation limiting your fire if you were in a contained house. And then you just witnessed flashover. That was flashover. You notice how everything just in the room ignited at once. But now our natural room, we're at 6 minutes, and we could probably still put this out with an extinguisher at this point. And we fast forward to 16 minutes. Now we're finally getting some smoke, but you could probably still put that out with an extinguisher at this point. 26 minutes, and we are still not even reached flashover conditions. 29 minutes, still nothing. They did a video like this about 15 years ago, same thing, side-by-side comparison. And in that one, the fire did finally reach an actual flashover, but it took, I believe it was 34 minutes. So huge difference in what we're putting in our homes today, and show you the amount of time you have to get out of your home.
Yeah,
Real
that's amazing.
Real quick, some other things just to want to point out is construction of our homes. These days, we use lighter weight materials like trusses. Trusses fail a lot sooner, which is not good for the people who are trying to escape the fire or as firefighters who are running in when everybody else is running out. So structure fires are dangerous. They have changed a lot as construction has gotten lighter and more affordable. Unfortunately, it's more dangerous when it comes to fires. And same thing with our contents that we're putting into them. Far more dangerous, faster burning, hotter burning, thicker, darker smoke with more toxins than we could ever imagine. Firefighters 40, 50 years ago could go in without breathing protection and just stay beneath the smoke. Today, we can't do that because, as you saw, the smoke gets down to floor level within a few minutes. So knowledge of these dangers and science helps us firefighters and the public understand some of these dangers. And hopefully new technology and prevention and detection, smoke alarms, smoke detector systems, suppression with fire sprinklers, and suppression with us as firefighters, and firefighter safety and fire safety for the public. Hopefully that new technology will help save lives all around.
That was really fascinating. We do have some questions here, Rick. I mean, that video of just the flashover, it's amazing to see how quickly that fire spread through that living room. It's impressive and not in a good way.
Right.
So we do have some questions. Judy would like to know, where do most house fires start and why?
There's a lot of reasons for house fires. The one that I think we see a lot of in the city of Binghamton is unattended candles, especially this time of year. People leave candles out. They think that, the pillar type candles and candlesticks are okay, but unfortunately they're not. As they begin to burn down, the wicks fall sideways out of them. They catch nearby items on fire. People leave candles unattended. The best kind are the jar type candles, but you should never leave them unattended, especially if you have children or pets around. They can knock them over, knock them closer to a curtain or a flammable material. Others are smoking. We have a lot of fires that are started by smoking, especially back porch fires, near garbage areas, back of the house. People throw a cigarette out a window, catches in a window down below. I've seen a lot of different smoking and candle fires. And then, of course, we have the occasional electrical or heating element type fires, space heaters, kerosene heaters, those type of things.
That actually segues to another question that we had. So how common are electrical fires?
They're not all that common if people are careful. Most common I see in electrical type issues is when people overload systems. Too many extension cords, overloaded outlets, overuse of extension cords, plugging extension cord into extension cord into extension cord. Seen quite a few of that. Usually, if you're careful, if you use the devices properly, you will not have an issue.
Great, thank you. Marion had a question regarding the firefighters cam video that you showed us. She wants to know, was the firefighter aiming at the source or at the ceiling to prevent flashover?
Okay, so typically what he was waiting for is he was waiting to hit the source to the room. In a real fire, we would be hitting over our heads to cool that down so it would slow down that potential of a flashover situation. But once they got to that room, for that particular training, he was hitting the base of the fire.
Thank you. So can you talk a little bit about what kind of masks or other protective gear firefighters use today versus years ago? How much has that actually changed?
Yeah, that's a good question. So it's kind of funny, the helmets that we wear haven't changed all that much since the invention of the old leather fire helmets, back in the mid 1800s. The shape of them hasn't changed as far as what most firefighters wear. There are more modern helmets out there. Some helmets have become more modernized, more dome shaped, and there's even new ones out there that look more like flight helmets, more like jet fighter helmets than anything, which give more protection to the firefighter. They're lighter weight, but firefighters, we are very traditional, and it's hard to get us to change. But so the helmets have changed a lot. The materials that our coats and pants are made out of have changed a lot. They're mostly fire retardant. Instead of having, they have a moisture barrier. So the outer shell is what is flame retardant. Underneath that's what's a moisture barrier, which keeps the water and the steam from getting into us. Years ago, those moisture barriers were impenetrable. They didn't breathe. So firefighters had a lot of heat stroke, heat injuries, heat-related injuries because they didn't breathe. Now those are breathable materials. Then underneath that, there's thermal barriers that help protect us from the heat penetrating and burning our skin. So those have changed a lot from the old, basically raincoats that they would have had probably back in, late as probably the 40s. They were still wearing basically rubber duck raincoats. And they didn't wear pants. They didn't wear fireproof pants back then. They would wear hip boots. They would pull up so they could keep them down below their knees. And then when they needed them to protect them from the water and the heat, they would pull the rubber boots up, but it still left their buttocks and their midsection under their long coats unprotected. So that would lead to burns. Firefighters also didn't used to wear Nomex hoods because they were usually beneath the heat. They could go in without the smoke, but as our fires increased, and as you saw in the flashover video, we're going into those types of fires now. We had to start wearing Nomex hoods. When I started, Nomex hoods were a single layer of material. Now they're up to 3 layers of material to help protect us from the heat. And then there's our breathing apparatus. Years ago, firefighters would wear filtering masks, which just help filter out the particulates. But then as the gases increased because of what's burning, the filtering didn't work anymore because you still can get the gas through the filter and suffocate the firefighter. Or it's an oxygen deficient atmosphere and it's not providing any air to them or oxygen, and they would literally suffocate because of the filtering mask. So today what we have is self-contained breathing apparatus. And all that is compressed air. And it's just going into our mask to keep us separate from the exterior elements that would be toxic to us.
Rick, how much does all of that weigh? I mean, you talked about there's a lot of different layers, and then you have your tanks on top of that. Once you are all suited up and ready to go, how much extra weight are you carrying?
They say that the average firefighter carries about 50 to 75 pounds of gear on them. So that's usually with, boots, pants, coat, helmet, gloves, hood, and the air pack, the SCBA. It's usually 50 to 75 pounds, depending on brand and stuff. And then, all the other equipment that we have to carry in our pockets. The laws even require us to carry a rope system now that we have to wear along with a harness to bail out of a building in case we do get trapped. And that's required by law. And it doesn't sound like much, but it's like an extra 7 pounds that we're carrying around. So as you add all that little stuff up that's required, it adds a lot of weight.
Yeah, that certainly does. So thinking about, what actually makes a really good firefighter, it sounds like you really need to be physically fit. How about the mental capacities or just being intuitive on fighting fires?
Yeah, so the physical fit part is really important. Actually, to be a career firefighter in the state of New York, you have to take what's called a candidate physical ability test. It's a very tough course that we all have to pass. Since I believe it's 2000, we all have to pass that test when we come on and get hired as a career firefighter. If you don't pass that, you don't get to be a firefighter. In the volunteer side, they have something similar in their Firefighter 1 course that they have to also pass because it's so physically demanding. And then the mental part of it, on the career side, we have to all pass psychological tests first, but that help decide how we handle stress. And because it is a stressful job, man. It's not just the fires, it's EMS calls, the rescue calls, all the other bad stuff that we have to see out there. But you have to be prepared for that psychologically, mentally, and deal with the after effects.
That is a lot to deal with. So thank you so much for all of the work that you and your colleagues do to keep everybody safe.
Thank you.
I want to ask about electric stoves and baseboards. Do those tend to be a little bit safer than propane stoves or fireplaces?
The only thing that makes electric stoves and electric baseboard heat safer is the fact that they do not produce carbon monoxide. So when it comes to carbon monoxide, only people who have gas-fired, propane-fired, or wood stoves in their homes need to have carbon monoxide detectors. Electrical appliances do not give off carbon monoxide. The only things that we see is if there is some kind of a problem, if there's been damage to the equipment and it hasn't been maintained properly, then it can be, a fire hazard. But normally operating it is just as safe as everything else. But the good thing is it does not produce carbon monoxide.
Do you experience much arson? Have you experienced that much in your career and in the Binghamton area?
We've had our fair share. It's not, I don't think it's as prominent as some people might think it is, but we do get the occasional arsonist, and don't see a lot of arson for profit or anything like that. It's usually most of the ones that I've experienced where we've caught and convicted the person is most of them have some kind of mental health history, and usually has something to do with that. And we've definitely had our share over my career.
So you talked a little bit about the open floor plan, which I found that really interesting, that actually makes the fire grow a little bit quicker versus having the house be a little bit more of a divided plan. Would you feel comfortable living in a high-rise building?
Well, it's one of those loaded questions. So most high-rise buildings, when we talk about buildings, we classify them by type. There's 5 types of building construction. Most high-rises are what we call a type 1, which is fire resistive, not fireproof, fire resistive. So they are compartmentalized from each other. So you could have a fire literally in one apartment, and the other apartments on that floor may only get smoke damage. They may not, the fire should not spread. The problem with high-rises is, for us, is being able to ventilate them. And then once you do take out the windows in a high rise, because you're at those higher elevations, now you have the issue of wind driven fires. And as I talked a little bit about flow paths, you've got a huge flow path because you have open elevator shafts, stairwells that the firefighters are trying to stretch the hose lines from to get to it. And those are creating flow paths. So once those windows give way, either because of the fire or because we need to take them out to ventilate, now you've got wind driven fires.
Great, thank you. Do you use a lot of the flame retardant chemicals on fires that you're fighting? And if so, does it have to be a specific fire to require that?
So we really use everything that we put out is usually water. We do carry dry chemical fire extinguishers for electrical fires and flammable liquid fires, carbon dioxide extinguishers, but for the most part, everything we use is typically water. There is foam available. We actually have a foam trailer in the city of Binghamton, courtesy of New York State, that we can use for large flammable liquid fires. Because flammable liquids, the problem with them is the flammable liquids, most of them like gasoline, they are lighter than water. So it just floats on top of the water if we use water. So you have to use foam so it floats on top of it so it extinguishes the fuel.
When you have an instance like that where you have to use the foam, does the DEC get involved after the fire for any of that cleanup, or what happens then?
Yeah, typically anything that's going to involve a flammable liquid is considered a hazardous material, so we will contact DEC. We'll use the county and our own hazardous materials team to help mitigate any runoff, and then we almost always call in DEC to assist us with that to make sure if there's any runoff that goes into the storm sewers and rivers, creeks, groundwater, that those are going to be addressed after the fact.
So you talked a little bit about having other calls that come through that aren't fire. How often do you get these calls, and what are they for?
Well, so in the city of Binghamton, we actually about 80% of our calls are actually EMS. All of us have to be EMTs or paramedics. So we provide ambulance service, we provide first response emergency medical service, and that is 80% of our calls. City of Binghamton Fire Department, we answer, I think, over 11,000 calls a year. And as I said, most of those are EMS. Then others are everything from carbon monoxide alarms, natural gas odors, power lines down, car fires, water rescue, rope rescue, car accidents, and then a lot of automatic alarms. Especially with a lot of student housing in the city. I still think that that should be the first class that every college student has to take, is like Cooking 101, because we answer, I would say, probably anywhere from 5 to 10 automatic alarms at student housing a day for burnt food, food basically setting off smoke detectors in the building. And that's a lot of our calls these days, believe it or not.
Well, it's just kind of double-edged. It's good it's not a full fire, but at the same time, it's taking time away from other resources.
Correct, exactly.
When you have extreme temperatures, either the extreme hot or with extreme cold, there's a whole bunch of different hazards. Do you ever have where the fire hoses can freeze up?
Yeah, we do have that situation. Not only the fire hoses themselves, but also the hydrants. I mean, the hydrants are our water supply. I mean, the trucks only carry 500 to 1,000 gallons each on them, and then after that, we are relying on the hydrant system throughout the city. And if hydrants start freezing up, now we don't have a water supply. And we're lucky that we have a water supply in the city. The suburban and more rural areas, they have to rely on bringing tankers in to bring the water in. But in the city, that can be a real hassle. And the hoses do freeze. And after a fire, we have to keep them even cracked open so they continuously are flowing. But still, as the ice forms inside the hoses, the diameter inside the hose gets smaller, so you're flowing less water. So it can definitely become an issue in cold weather. And then just slips and falls from the ice that forms when we're using water everywhere. As it freezes, firefighters slip and fall and get hurt.
Yeah, that's not good. Well, as we are going into these colder months, something to keep top of mind. If somebody wanted to find more information about what we heard from you tonight, where can people go?
So if you want me to, I can put it in the chat and you can post it to everybody. But City of Binghamton Fire Department, our website, we can put that out there. And then National Fire Academy and NFPA have some great sites for fire home and safety information also. And I believe I've already sent you a few links on some YouTube videos that are also helpful for home fire safety.
And we did pop some of those in the chat earlier today, and we will get the Binghamton City Fire Department's website in the chat as well. Thank you so much, Rick. Brian, I want to wrap things up with you. Where can we go to watch The Devil's Fire?
You should be able to go to WSKG.org and search for The Devil's Fire, and I believe you should be able to view the whole film there.
Super. Thank you so much. I would like to thank our guests, WSKG filmmaker Brian Fry and Binghamton City Assistant Fire Chief Rick Allen. Thank you both so much for being here with us tonight.
Thank you, Nancy. Thank you, Brian.
The Devil's Fire will re-air on WSKG TV on January 1st at 3 p.m. And as Brian mentioned, there is a link in the chat that will take you to the full-length film that you can watch. Our next Science Pub is on Tuesday, January 11th with Dr. Jan Roberts on cannabis and women health. Dr. Roberts will discuss the science behind the endocannabinoid system and how its potential can be harnessed to treat common medical issues facing women today, while also exploring the risks and rewards behind this frontier of plant medicine. So join us for cannabis and women's health. The link to RSVP is in the chat. You can watch past Science Pubs through the WSKG app, on demand on your smart device, and on WSKG's website. Be sure to like our Facebook page also for future events and for science updates. I'd like to thank our WSKG team tonight, our director, Alyssa Micha, our chat moderators, Patrick Holmes and Christine Kieswer, our science intern, Julia Diana. Thank you all so much. Thank you, Brian and Rick. This was a wonderful talk. I'm your host, Nancy Coddington. Thank you and have a good night.
Thank you.
Thank you.